Hello everyone. In continuation with our previous discussion on corrosion measurement, so if we recall our previous discussion, we have talked about different corrosion measurement method such as weight loss analysis, then surface analysis of corrosion material, then the corrosion product analysis, and then we learn how we can apply the electrochemical methods to do the corrosion analysis. So we have divided into two categories. The one was when we are applying that DC current and measuring the change in the voltage, and particularly we call it polarization based methods. And the second one, when we apply the AC input and we measure the change in the voltage, and that is commonly known as impedance analysis or electrochemical impedance spectroscopy, EIS. So in the same direction, today I am going to talk about the two topics. One is the corrosion. Basically, we are going to measure based on the change in the electrical resistance. And the second topic is there are various methods which are basically comes under the umbrella of non-destructive techniques. So though these topics are not listed in our course, however they are very important and they are basically the part of corrosion measure. So I just would like to give a very brief detail about these. I am not going to discuss each and every component or aspect of these methods. So let's start today. So electrical resistance technique. So it's a well known, like when we are measuring the resistance of any device. So if there is a corrosion is happening of a metal, then with respect to time duration, there will be change in the electrical resistance. Why? Because if we are measuring the cross-sectional area of the device, so if the corrosion is happening due to the time and when the material is exposed in an environment, then the thickness of that material is reduced and the cross-sectional area of that metal is becoming smaller. So if the resistance of the material or the specific resistance of the material is become same, then due to the change in the area, there is a decrease in the electrical resistance. So how this reduction or decrease in the electrical resistance happen, or we can say the change in the electrical resistance happen, if we can measure that change, then we can give an analysis or we can have an idea whether or what kind of degradation in the material is happening. So electrical resistance of a sensing element or probe is exposed to the environment of the interest. So let's say we are interested to investigate a metal, how it is going to degrade in a particular environment. So just use the same metal as a sensing element or a sensing probe and design in a specific manner. I will show later. So then you can use that and use this material as a probe and expose to in the specific environment in which you are willing to test it and then see what kind of changes happen in the resistance. So as we know, there is a decrease on the cross-sectional area, thus measured electrical resistance will increase. And what are the methods or how we can do that or where we can apply this method? So there are a variety of sectors such as oil and gas production, pipeline, chemical process, pulp and paper industries. This method is commonly utilized. Power generation and archaeological preservations. In these sectors, this electrical resistance method or electrical resistance technique is commonly used to understand the corrosion. And this method is quite simple because it's just we have to measure the electrical resistance, and so maintenance and relatively easy. Also, the data we can easily predict because just a simple IV profile is there, and we can get the realistic data or real-time data. So even if we are interested about the investigating the reliability of the product or maybe of a structure, then of course we can deploy this technique and we can do that. So here we can understand a sensing probe design. So let's say it's a simple structure and where we are having a cross-sectional area A and length L. So even A multiplied by L we can see the value. And so if we consider this top surface is going to be corrode due to the environmental exposure. So this thickness or the area of this probe will reduce with respect to the time. So if we are applying a fixed voltage across these two terminal, current in, current out is showing here. So what is the voltage drop across the this probe we can measure, and that will give an idea about the corrosion, or we can see the electrical resistance, and that we can measure by using this formula. It's a well-known formula: R is equals to rho L into A. Sorry, rho L by A, where rho is our specific resistivity of the material, L is the length, and A is the cross-sectional area. So if we know these parameters, L, A, rho, then we can calculate R, or we can calculate whatever changes are happening in R with respect to the time when the material is exposed in the environment. So these are the common design of the sensing probe. So here you can see it's a full setup is here where these are the probes, and probe could be like they are connected with different kind of wires to measure the electrical conductivity, and the probe design could be anything how you are going to measure electrical resistivity. So variety of different design of electronic circuit or this basically resistance probe can be there. And the next PPT, I'm going to discuss at least one of the idea how this electrical resistance method can be applied. So typically, whatever the components are there in the sensing probe, of course, we need the wires and loop to just fix the wire and connection. Then tabulars, then thin film on the seed, basically the particular material on which we are thinking to the degradation is going to be happen, or the seed for which we are going to measure the corrosion. So and then the strips. And again, as we discussed, like where we can apply in variety of industry like chemical process, oil and gas industry, concrete structure, atmospheric corrosion in soil. So this is the one example which can give a little bit clarity about this method, and we can understand how the technique is utilized. So electrical resistance technique, and this work was published in Census 2019. The title was Development of an Electrical Resistance Sensor from High Strength Steel for Automotive Applications. Means the high strength steel that is itself used in design of automotive the vehicles, and how this steel is going to basically behave once it is exposed in such kind of environment. So this study they have proposed here. So sensor material is here high strength steel, similar as the part produced in automotive industry. So the material is the same whatever used for the making the product in the automotive industry. Similarly, here, real-time corrosion process, they are willing to measure. Moreover, your probe tip is basically located inside the vehicle, and which is also having the connection or equipped with the data logger. So data can be stored there, and which is also enabled to transfer the data, wireless transfer the data to basically do the routine measurement or time real time monitoring or measurement. So the three setup is there. Your probe is in the vehicle located in the engine side, then it has the data logger as well as it is also having the wireless transfer system, so basically achieve the real-time monitoring. And also, just to give an idea, so the same time similar material was also tested electrochemically to get an basically comparative study and just to have a verified the result whatever achieved in this experiment when we are adopting the electrical resistance technique. So both the things are compared also. And this is the general setup. Like if you see a car here in which the engine side they have shown like this kind of probe is there, which is located inside the engine, and the data logger is also there, and then it has some kind of communicating device which is able to send the data. So it has a sensor unit, data logger, and communicating device. So this is the typical structure of the sensing probe. So sensing probe were fabricated from H800 high strength steel, and the structure is look like they have basically 4 different compartment of resistance measurement. You can see the Rx, then the reverse Rx opposite to this, then R opposite to this another R, and then they are measuring basically applying the current in this terminal and this terminal, and they are measuring whatever the voltage difference is happening in terminal. Let's say this is the terminal 1, this is the 2, this is the 3, and this is 4. So they are applying the current in terminal 1 and 3 and measuring the difference whatever we are getting in terminal 2 and 4, that is delta U. So in B figure you can see how the device is there. So if you see, this is the one resistance unit, this is the second resistance unit, similarly this is another one, third one, and this is the fourth one. And this top is shows just a metallic contact, and the bottom side, if you see this seat is there, right, the bottom side. So this seat is basically the stainless steel or high strength steel seat, and top of that they have made the contact. So contact is made in such a way like this kind of circuit structure should be there. So the electrical resistance sensor made of high strength steel from a 250 micrometer thick foil, and the 4 sensor elements were arranged in a Wheatstone bridge. So if you remember, in Wheatstone bridge means we can accurately measure the resistance of a unknown circuit. So let's say if we know the resistance of this R, and this R, all these 3 leg, then we can easily calculate the resistance of the 4 leg. So this was the basic idea here. This kind of circuit was designed, and the 2 of the sensor element were exposed, where the other 2 was basically protected by the transparent epoxy layer. Okay, so see how they have basically performed the calculations and all. So as we know, R is equals to rho L by A. So constant decrease in the thickness of metallic conductor cause an increase in the electrical resistance. So the 2 probe which are basically exposed in the metal, there will be a change in the electrical resistance, while other 2 probes which are basically coated with the epoxy is not going to expose in the environment, so the change in the electrical resistance will not be there in that case. So we have a comparative study, and then we can get whatever the differences are there. So then we can say if we multiply resistance versus area, then of course it will be constant, because with respect to time there should not be any change, because L and rho is the fixed. Length of the material is fixed, and of course the rho is fixed. And ER sensor, the 4 sensor element is here. So in case of Wheatstone bridge, so let's say R and delta R change, whatever delta R change is happening, this is happening due to the reduction in the delta A. So again, if you see, this is the overall resistance after some time, this is the overall area after some time. So multiplication of this will be always equal to the area and the resistance. As you see, R into A is constant value here. So this will be applicable here. And 2 of the sensor element are protected, and 2 are exposed. So basically now the difference, and so delta A we can say from this equation, this one, it can be written as A into delta R plus delta R. Means if we know the change in the resistance and we know the resistance at the beginning, then we can calculate delta A, and all these quantity are known. You know the initial area, cross-sectional area, you know the initial resistance of the material, and then you also know the delta R, the change in the resistance. So we can easily calculate the delta A. Now assume the sensor corrode uniformly. So delta R can be written as delta R is equals to Rx minus R. Basically, if uniform, then whatever the resistance change is happening, that is whatever the difference with, because one set is protected with the epoxy layer and one set is basically exposed in the environment. So whatever the difference between these two, that is equivalent to the change in the resistance what we are getting. And the relation between U, delta U, this is basically the voltage whatever we are getting initially, and delta U is the voltage whatever happened due to the change in the delta R. Okay, so it can be written as delta U by U is equals to delta R into 2R plus delta R. So U is the output potential of the bridge and delta U is the potential drop on the Wheatstone bridge. Right. So this is the mathematical formulation. Basis on it, we can calculate the value of R and then we can think of the corrosion. So change in the thickness, similar manner we can say delta D is equals to D naught into 2 into delta U by U 1 plus delta U into U. So delta D is the change of the thickness and D naught is the expected initial thickness. Remaining thickness D and change in the thickness is basically relevant to each other. So proportional to D. So if we know the delta D, then we can also calculate the corrosion rate. CR can be defined as the derivative of the additive inverse of the remaining thickness of D with respect to the time. So V corrosion can be calculated minus delta D upon dt. So if you can calculate delta A, then we can calculate delta U. Then if we can calculate delta U, then we can calculate the change in the delta D. And if we can calculate the change in the delta D with respect to time, then we can calculate the V corrosion. So these are three parameter delta R. Based on the delta R, we can calculate delta A. Based on the delta A, we can calculate delta U. Based on delta U, we can calculate delta D. And if we know the delta D value, then we can calculate the corrosion rate. So the resolution of ear measurement is as good as 0.5 micrometer per year. So this much resolution we can achieve in this technique. Here is the data of this experiment. So basically monitoring of U and delta U and the thickness reduction of the readout data for sensor 1 and 2. So there was two sensors, right? So the first sensor was exposed, the sensor 1 was initially exposed in the summertime. So they achieved the red curve. Then till here, almost 5 to 6 months. And sensor 2 was exposed 5 months later in the winter time. So then second was exposed just for 2 months here after 5. So this is the U by mu, this is the delta U. So if you just compare the delta U, so here basically there is a difference because this sensor is not exposed. And even D by micrometer, so if you can see the change in the T, so this is these two are different. Blue curve is basically in the winter time, and red curve is basically happening due to the exposure in the summer time. And this difference is here. Similarly, the reduction of the thickness of the corrosion sensor exposed for 6 months shown in the red, of the exposure for 2 months in the blue curve. And this is just a placement like where the sensor was placed inside the engine, and they just measure delta D by delta mu. So you calculated U, then you calculate delta U, then D, and then delta U by micrometer with respect to the time. So if you know these values, then they have calculated the average corrosion rate in different section of the measure data of sensor 1. So if you remember, based on that previous data, they calculate sensor 1, sensor 2, sensor 1 in summer, sensor 2 in winter. and then after fitting also. So sensor 1 is summer, it is around 0.002 micrometer per year, and here it's 0.4 micrometer per year, but in winter this is even higher. See, the first sensor, the red one is the first sensor when it is exposed in the basically winter. So 1.84 micrometer per year, then it's further increase and further increase, something like this. And in case of sensor 2, this is almost 0.056 micrometer per year. So which is slightly different as compared to the sensor 1, because they both are exposed in different time period. One was exposed in summer side and another is in at the time of winter. So the thickness of the sensor were adjusted to the value of 250 micrometers so that both the sensor could be compared, and they just use basically 250 micrometer thick sensor. So why they have basically achieved different corrosion rate? Because both the sensor was not exposed in the same environment, they were exposed in the different environment. So this was basically the basic idea about the corrosion measurement using electrical resistance method. So there we are basically focusing about whatever the overall change in the electrical resistance, and if we know that value, then we can apply the mathematical calculations and then we can get the idea what kind of changes there, how the corrosion is taking place, and the real-time monitoring is also possible by applying that method. Now the next method is non-destructive techniques or the technologies. So this is not a kind of one method. There are a couple of methods which can be utilized to do the non-destructive analysis. So basically our material is not going to expose any destructive or in that setup where the material is going to have some harm, or where we are going to basically accelerate the corrosion rate, or it is going to increase the degradation or any other kind of effect is happening. So if that is the case, so most of the time in industrial applications or where exposure of any environment or any external things are critical, then this kind of non-destructive technologies or methods are preferred. So here I will just give very short brief about different technologies just to have an idea. So what we mean by basically non-destructive technique, it is basically used to access the integrity of a system or component without compromising its performance. Means we are not going to basically stop any working conditions. We no need to basically put any external circuit or any technique where your component is going to basically expose in some additional environment. So without compromising its performance, we can do the analysis. And here the things are a little bit different. Like here we use variety of sensors, then whatever data we are getting from sensors, that data analysis is required. And analysis, for data analysis, maybe we need to do the modeling, we need to convert this information, then we have to compare with what kind of material is there, what were the material synthesis, and then what even the technique was adopted when we are using the material design. Because though the material is same, but all these things are going to be affected. Then what is the service life, whatever the performance, whatever the basically different conditions can be there in the system. So that variety of different aspects need to be understood, and then we can at least assess the corrosion by using non-destructive technologies. So if you like to categorize, we may say non-destructive evaluation method can be say like visual inspection, just by looking. If we can see it, like say very seriously visualization by putting some light or by some optical microscope or some magnifying image, if we can see it, so just by visual inspection we can do the evaluation. Or liquid penetration inspection, let's say just penetrate the liquid in the area where we are expecting some kind of corrosion is there, and then understand what is there. Or by inserting the magnetic particle, how it is behaving, if your material or your structure is having some magnetic susceptibility. Then by using X-ray or the gamma rays, and then whether it is material is absorbing any X-ray or the gamma rays, or it is having some kind of analysis. Electromagnetic inspection and ultrasonic. So either using electromagnetic wave or ultrasonic wave, we can also do the analysis or thermographic. So basically temperature based analysis. So these different variety of tools can be applied, and then we need to analyze the data, and then we can basically say a non-destructive evaluation method has been done to understand the corrosion. So this can give a broader picture of how these non-destructive technologies are adopted. So NDE method, like I discussed before, what kind of tools are there? You use any of the tool and just get the data. So we may have sensors or some other things to collect the data, then data acquisition. So basically use this method, apply some sensors, data acquisition unit, and get that data, and then based on that data, decide the non-destructive equipment parameters. Because based on these parameters, we need to do the further analysis. So correlation, modeling, and further analysis of the data. And then this thing should be correlated with the material engineering. Like what kind of material is there, what kind of defects parameters are there, and what was the material synthesis protocol. So based on these things, then if material is there, then whatever their fracture mechanism, life cycle, ion management, and if we get this data, then overall correlation need to be established, and reliability engineering is also need to be assessed, performance and service life. So whatever the up and down or whatever the change in the condition of the service, that need to be understood. If we can get all these parameters, then we can have an idea about the basically the corrosion assessment. So result depend upon the various parameters, because this technique is basically depend upon lot of different component. So whatever data is basically we are getting with the non-destructive technologies or the methods, it will vary based on the different conditions. So maybe the same system will access by one team of expert can have different set of data or can have a different results which is accessed by the different set of expertise. Why? Because there are different components. Maybe we are having the material composition, whether it's magnetic or non-magnetic, metallic, non-metallic. Similarly, though the material is same, but what is the part thickness, the size, the geometry of the part, which are having some tendency of corrosion. So if the same material is there, but there is some change in the size, geometry and part, then of course there will be a difference. Then material conditions, heat treatment, grain size, fabrication process, then how slow or fast or how we are basically applying these non-destructive tools to doing the data analysis or to basically getting the data. Similarly, the fabrication method, how the material was fabricated, casted, forged, welding, any adhesive or brazing. Then whatever the material, surface condition, the roughness, plated, or if any scaled are there or something. Then nature and use of the part, whether it's a critical or not critical, high or low stress, human factor, like who is doing the test, how it is operated. So many of these parameters is basically affecting when we are doing the corrosion analysis using the non-destructive technologies. So one of which, as we saw, a couple of different tools, so like visual inspection. So this is very common, and the old method also. We just need to inspect the corrosion by just doing either visible light reflected from a surface, revealing some of its feature, by observing the appearance of the part, let's say the change in the color, or maybe the appearance of some kind of surface product of that material, or if you can visualize any kind of thickness change, dimension change, the appearance of the part, just we can see and then we can think. Because let's say in our household things, let's say the door or the handle is rusted or something is happened, the thickness is reduced, then we can just by visualizing we can say if there is some kind of corrosion is happening here, what is the life of the material. So that is the appearance of the part. Then basically surface corrosion, exfoliation, pitting, internal corrosion can be detected visualizing when proper access to the inspection area is obtained. So this kind of analysis is done, and its reliability depend upon the ability and the experience of the inspector. This is the important, like who is doing that inspection. The expert is there, so how whether it's experienced person is there or his ability. So these things are going to matter. Then visual inspection, many way, either directly or remotely by using boroscope, fiberscope, or video camera. So maybe we can do on site or maybe the remotely. So all these things are possible that people are doing. Other is liquid penetration inspection. Means if there is any kind of capillaries formed or sometimes cracks are there, and if we are not able to see just by visualization, so how we can do that? So then the liquid penetration method is required or we can use. So this technique is again easy and not so basically different experiments are required. Just need basically some kind of portable systems, and this is also a little bit accurate also, and detect open to the surface crack indication. But if we are willing to understand the surface cracks and the capillaries, then the cleaning of surface is very important. Let's say the outer surface is covered with the dust or maybe the corrosion product, or it is having some kind of any external product and which is basically having a covering of that surface, then we will not be able to get very accurate data. So the surface should be cleaned very rigorously to get a proper data. It really detect any open to surface cracks, surface defects, and pitting. So at least these three kind of surface cracks, surface defects, and pitting can be easily identified by liquid penetration method. The next one is the magnetic particle method. So here applied to the detection of surface connected or near surface anomalies in test objects that are made from the material that sustain a magnetic field. So if the material is basically having some susceptibility for a magnetic field, then this kind of method is applied. So here we basically use the magnetic particles and flow these magnetic particle inside the this kind of test system, and then we require some kind of magnetization power source. So maybe we can use the electrical outlet, and here in this method the most frequently used is evaluating the quality of weld deposits and subsurface weld indications such as cracks. So the welding part or maybe there is any crack in the welding, so that if that material is magnetic susceptible and we are putting the magnetic material, so the magnetic material will basically can give a kind of signal where the cracks or that joint or the weld failure is there, that can be identified. Then the radiographic method. So this is again very good tool, and I think this is the also utilized in a very long extent in industry as well as in the laboratories also, and it can give a very good data about the surface and surface discontinuities. So here either they use the X-ray or the gamma rays. So you can produce X-ray and the gamma rays and just pass these X-ray and gamma rays from the material and just see whatever the penetration rate or how these X-ray and gamma rays are basically penetrating through the material. So whatever the absorption is there, so whether they are absorbed or not. So depending upon the type of material, so what is the density of this material and the thickness, the absorption will be different, and based on this we can have an idea about the corrosion. So recording the differences in absorption of the transmitted wave, variation in the material can be detected. So variation in the transmitted wave may be recorded by either film or electronic devices, and then it can be analyzed. Next is the Eddy current. So an electrical conductive material under AC magnetic field that is generated by a coil of wire carrying an alternating current. So Eddy current are induced here on and below of the surface of the material. So at the surface of the material we are basically getting the Eddy current if you are applying the AC magnetic field. And these Eddy current in turn generate their own magnetic field which oppose the magnetic field of the test coil. So measure the change in the impedance. And ED current are sensitive to change the electrical conductivity, change in the magnetic permeability, the geometry or the shape of the particle being analyzed and defective. So basically, we are applying an AC magnetic field, generating the ED current. ED current is generating their own magnetic field. So based on the change in the geometry of the material or the surface of the material or the defect, there will be change in the ED current. So if that change we can just measure. So whatever the ED current at the beginning and then whatever the ED current when there is some degradation happening in the material, based on that kind of difference, we can understand if there is any change is happening or the corrosion is happening in the material. So effect of cracks, inclusions, porosity and corrosion can be understood. Similarly, ultrasonic method, one of the most widely used technique. Here again, we are generating the ultrasonic wave. So sound wave through a piezoelectric crystal at a frequency between 0.1 to 25 megahertz into the specimen and analyze the return signal. So we are generating an ultrasonic wave. That sonic wave is interacting with the material and then it is returning back. So whatever difference we are observing at the basically initial state, and then when the material is basically get corroded or it has some kind of degradation, whatever difference is there, that difference gives the understanding about the corrosion. So the device measures the time it takes for the signal to return and the amount and the shape of the signal. And portable device probe will be direct contact with the clean surface to order to obtain the accurate information. The most fundamental technique used is that of thickness testing, and the time flight is used to establish the thickness. Then the next one is the thermographic. So here the test objective must be thermally conductive. So then how the thermal conduction is happening and the test object surface must be reasonably uniform in the color and the texture. So use the infrared energy associated with the part or system being examined, and then you just measure the infrared based detector based system, like whatever the change is happening in the thermal propagation. So give a photographic image of the thermal condition present on the surface being examined. So if there is any defect or the crack or any irregularities in the surface, then there will be difference in the basically thermal condition. And that by looking the photographic image, which is based on basically the thermal condition, we can get the idea about the surface. So used to accurate measure the metal temperature to establish whether brittle or overhead condition exists. Many defects affect the thermal property of material. So therefore corrosion, debonds, crack, impact, damage and panel thinning can be understood. So this was basically a quick overview about these two methods. First was the electrical resistance and the second was the non-destructive technologies. So here I just given a brief idea so that you should be aware about the other methods, how they can be utilized or whatever the basic things are there. And if you are interested, you should read detail in textbook or some research papers. So today I will stop here. Thank you very much.